A girl flies a kite with a string at 30-degree angle to the horizontal. The tension in the string is 4.5 newtons. How much work does the string do on the girl if the girl stands still, runs a horizontal distance of 10 meters away from the kite, and C, walks a horizontal distance of 20 meters towards the kite? Ooh, look at that. That's a typo. It just walks a horizontal distance of 20 meters toward the kite. So let's go look at this thing. So again, it's the picture that's most important here. So when I look at my picture here, I'm going to imagine that we have a stationary girl. What does stationary mean? Well, we immediately know here is that since no displacement is occurring, there is no work done. Now we're talking about the girl with the kite. So what I want to do here is that I want to sketch the situation. And draw a bar diagram. So I imagine that we have a kite and it's flying. So let's say this is the kite here. And typically with the kite, we know it needs a tail. And in the old days, we used to tie ribbons on them. And the reason why that kite is flying is because we know there's a wind that's doing that. So now I got to draw my girl, and she's got to be stationary. So let's see here. So I could imagine, here, let me get at least some sense of what's going on here. Let's say that this is the string and it's coming down. So she's going to be down here. So I could imagine that she's probably sort of like pushing back. Uh-oh, looks like my string's going to be wrong here. And then we need her arm. And then the kite attaches to that string. And then we see her other hand right there. And of course, she has a blue dress. And what we know here is that she is stationary at the spot. So the first thing I got to do here when I draw this situation is that I imagine that I have the girl. So now what I'm going to look at is I'm going to look at a free body diagram. And I imagine that I have a sketch of this girl here. And what we know here is that there's a tension force that's occurring at an angle of 30 degrees. And when we're thinking about work here, we know that the displacement is zero because there's no motion. So now, when I'm looking at this thing and I'm saying, yes, I want to focus on this girl here. Yes, there is an external force, right? We are going to say that there is this tension force that's external, but because the displacement is zero, there's no work being done. So now, if I start to think about it in the following way here, we then say that the work energy theorem tells us then that the net work done, in this case, this is the work done by the tension. And here we have this tension, and I guess we'll just say that this tension force, let's not do that, times the displacement. And immediately we see here is that this displacement right here is 0. So therefore, the work is 0. And that tells us then that the change in energy of the system is also 0, which tells me then E1 is equal to E2. In other words, we have an equilibrium situation of energy. So we have an equilibrium of energy. So according to our bar diagram, how do I want to draw my bar diagram? I'm going to say, okay, so I have this amount of energy to begin with. This is how much energy I have. Now remember, of course, that energy is meaningless. And then we do a certain amount of work. In this case, we say that the work of external work is 0 because there's 0 displacement. And as a consequence, we then see that the energy of the system did not change. And they're exactly the same like this. So there's no change in energy. Now, if I come back up here, now the girl runs. Okay? The girl runs a distance of 10 meters. So let's go look at this situation here. By the way, I should be saying that the combination of these two should be exactly the same. And that's because the work energy says that E1 plus the external work has to equal E2. And since this external work here is 0, it does not change the energy. So now let's go to B here. So in this situation, I probably should have copied this. I didn't think about this. But what if I bring in, oops, I didn't really prepare enough apparently. But let me copy this and bring it in. So if I place in, this is the question that's being asked in B here. Now what we know here is that the girl runs a horizontal distance of 10 meters. And then the question is, what does running have to do with the work energy theorem? And the answer is nothing. That is a decoy. Because when we look at work, work is not about that. Work is about force times distance. So in this situation, we now have a girl that's running away, but it does not matter. All we know is that a displacement is taking place. So running implies a displacement now occurs, and therefore the external work is not equal to 0. So then we start the same process here. So you know what? I think I'm going to take the kite with me. So I don't have to keep drawing the kite. Let me see if I could copy that. So let's do the, so here's my kite. It's in this situation. So now what I need is that I need a girl that's going to be running. So what do I imagine here? I imagine that she's taking nice big strides. Okay, that dress needs to be a little bit better. And we imagine here that as she runs, she is hanging on to the kite like this. Uh-oh. Let me draw that a little bit better. So we know that she's running because she has a velocity in this direction. So we could say we got a kite. And so now we ask the same question. Before, what was our question? Is that draw a situation. And that means I need a free body diagram to see what the force is looking like here. So in this situation, so if I look at my free body diagram here, what I'm seeing here is that I could take my picture of the girl here running, and if I place it right over here, what I'm seeing here is that I'm seeing this. There's a tension force. This is my tension vector. And now I have a displacement in that direction. So now that means I have to break up these forces into components. And what I see here is that only forces parallel or anti-parallel to the displacement are going to contribute to the work done here. And what you're seeing here is that if I pick my displacement to be in the positive direction, I literally see that the only force that matters is Tx because that's anti-parallel. However, Ty is perpendicular. So in this case here, we see that Tx is anti-parallel. The D, which then implies that the work done by Tx is then negative. Ty is perpendicular to D, so that tells us that the work by Ty is 0. So I only have to contribute to one of these things here. So I only have one term here, and so what I'm going to see here is that if I calculate this work, what do I find? I then find that the work in this case of Tx, by the way, I should have said this here. This is the work energy theorem. That then the work, and what I'm looking at here, the work where external to the girl, just like we did before, this external force in this case is going to be minus the tension in the x direction times the displacement. So when I'm looking at this, then I find here is that I know that this has to be minus t cosine of 30 times the displacement in this case. And in this case, they tell us a couple of things. We know that the tension is 4.5 newtons, and the displacement in this case is 10 meters. So if I plug in all my numbers here, times a distance of 10 meters, then I'm going to get a work that's minus 43 joules, and that's going to be the work of Tx in this situation. So mathematically, it does that. Picture-wise, what does that mean? Well, again, energy by itself is meaningless. So all we know is that this kite is reducing the available energy to the girl. So the work of the kite on the girl reduces her energy. So picture-wise, we could imagine that she starts at a high energy, and we're going to call that E1. And then what's going to happen here is that there's going to be negative work. This is going to be negative work of Tx here. And the only thing that matters here is that Tx reduces the available energy of the girl, lower energy right here. So what is meaningful? E1 and E2 are meaningless. So think about it. When you say you're low on energy, physics-wise, that has zero meaning. It means nothing. So we say this guy right here is meaningless. We say this guy right there is meaningless. So what is meaningful? It's this reduction in energy. And it's this reduction, which we call delta E, that is equal to negative 43 joules. So then we say that quantity is meaningful. That's what makes energy abstract. It's an abstract concept. It really, really is. Okay, let's go to C here. And in C, we had a similar situation where this time she walks this time. So if I plug this guy into here, she walks a horizontal distance. Just like we said, what does running have to do with the work energy theorem? Nothing. Once again, walking has nothing to do with the work energy theorem, other than a displacement occurs. Because it's not in the definition of work. It's not in the definition of work. So then we play the same game. So as before, what I'll do here is that I'll grab this kite and we want to draw the situation again. So now the difference here is that the girl here is now running towards the kite. So if I'm looking at this, we could imagine that we have this scenario here. No, she's not running, she's walking. Right? And then So she's moving now in this direction right here. So when I look at this thing here, what we're imagining here is that she is grabbing on to the kite and is moving towards it. Maybe you'll do something like that. So again, we do our free body diagram to find out what do we mean by the work. So if I now draw my free body diagram, I go, okay, so what's happening? I have an external force acting on her. What is the external force? Again, it's this tension. The big difference here is that now the displacement is in this direction, which I didn't put in here before. So now we've already concluded that the only force that matters here is this Tx here. So just as before, we can see here is that Tx is parallel to D, which then means that the work of Tx in this case is positive. So we know that there's an increase in energy here. So then we start our calculation here, and we then say that the work energy theorem then says that if I have external work, and in this case, it's the force, the work of the tension, which then will give me positive work, force of Tx times the displacement, then this quantity is going to be T cosine of 30 times D. And again, the only difference here is that now the displacement in this situation, we now know is larger. So it's 20 meters. So when I stick in my numbers here, we're seeing here that now this is going to be 4.5 newtons times cosine of 30 times 20 meters. And then I get a value that should be twice as much as the previous value. I don't know what I wrote. So if this is 43, this should be 86, assuming that my numbers are good. I hope my numbers are good. It should be double that. So then this should be 86 joules, and that's the work of Tx. But again, just like we said before, we see here that the work in this situation reduced the energy of the girl. In this case, we could then say here that the positive work of WTK increases her energy. So then, picture-wise, what we do then is that we come back and we just say, okay, so now what happens? I have this amount of, this amount of energy. And that is a meaningless number. Now I do positive work. In this case, my work is double the amount of Tx because there was twice the distance. That's a little bit too close. I'm going to move this down a little bit. As a consequence, I should have a higher energy after the work interaction. And again, what is meaningful? Only this delta energy. This is the only meaningful thing. Right? All of that work, right, that tells us here is that all that work, Tx, does not disappear, but reappears as stored work, which we call the change in energy. We do not say energy, that's the change in energy.